Hi everybody, this is Dr. Niger with a Physics Fundamental Screencast. This one's going to be first in a series of screencasts dedicated to projectile motion. This particular video is going to look at problems where the object moves up and outward at the same time and lands at a height that is different from the height it was launched. All right, so let's start by talking about this idea of projectile motion. All right, this is two-dimensional motion, all right, and it's motion with horizontal and vertical changes. And those changes happen simultaneously. All right. The key here is that even though there are two dimensions, they act separately. All right. And that's going to be a really important concept to keep in mind as you work these problems. All right. So that means that these two dimensions must remain apart in our calculations. All right, and I have a organizer that I like to use that I'll show you in just a second to help with that. All right, so what does this look like? All right, so let's say we have some height, all right, and on top of this height is some object, all right, and for these particular problems, the object's going to be fired up and then it's going to come and land on the ground. There's the ground. All right, so there are a couple different variables we're going to be working with. We have the height of the cliff, and this is the change in the vertical position, so it's the delta y. We're also going to have how far out from the cliff the ball lands, and because this is a horizontal distance, this is our horizontal displacement, or delta x. All right. In addition, we're going to zoom in on the beginning portion of the ball's motion. All right, so it's going to be moving upwards at some angle. All right, this is going to be our resultant velocity, and that the resultant velocity is made up of two components. All right, this is going to be our x component of that initial velocity, and this is going to be the y component. All right, and then of course we have our angle theta. All right, so we can use our sine, cosine, and tangent trigonometry functions to help solve these different components. All right, we're also interested in what that motion looks like as the ball lands. All right, so it's similar. You have the object landing, except this time it comes down. All right, so it's going to look a little bit different, but we still have our x and y components. Right, we've got our velocity in the vertical dimension, and we've got our velocity in the horizontal. All right, so a couple things to keep in mind while we're working these problems. Hold on, I'm going to shrink this stuff down just a little bit to give myself a little more room. The first thing is that vertical motion is free fall. All right, as the ball moves upwards into the air, gravity is acting on it. So it acts just like any other object in free fall. All right, so we're going to get a changing vertical velocity due to the influence of gravity. All right, so that means we're going to have changing velocity. So we've got acceleration, and that means that we're going to be using our negative 10 meters per second squared quite a bit. All right, second, the horizontal motion is constant. All right, so that velocity in the horizontal does not change. Okay, and that's really important to keep in mind when we're working these problems. Okay, so let's try one. All right, here I've got a baseball player who hits a ball upward at 23 meters per second at an angle of 55 degrees above the horizontal into the outfield stands that are 10 meters high and 94 meters away. Okay, so I always like to start with the picture. All right, so let's just start with a picture of what's happening initially. All right, we have our ball that's being moved into the air, and we're going to have two components to that motion. All right, but we're given the velocity is 23 meters per second, and that is our resultant velocity. That's the velocity is actually moving, and an angle of 55 degrees. All right. Now, the organizer that I like to use is pretty simple, all right? Change in position, velocity, acceleration, time, all right? And then I usually put the resultant velocity and theta in here too, all right? So I make my rows and columns, all right? And I give myself two columns here. One is the X column, so that's my horizontal, whoops. And then one is my Y column, but I stop after acceleration because the time is the same no matter what dimension you're in, and so is the initial resultant in theta. All right, now I can fill in a couple pieces of information just from the get-go. All right, I know that the horizontal motion is constant, so there's zero acceleration, and I know that the vertical motion is dependent on gravity, so I can fill in negative 10 meters per second squared. Because the horizontal motion is constant, there's no v final or v initial, but there is for my vertical motion, so I tend to put in this diagonal slash, and I use my initial and final areas, all right? Now I can fill in the information that was given, all right? So I have something that's moving at 23 meters per second at 55 degrees, and above the horizontal, we're going to just call that north of east, okay? We also know that the outfield stands are 10 meters high, so that's the change of position vertically, so that's going to go on the vertical column, and that those stands are 94 meters away. So that's going to be our range, also known as our horizontal change in position. All right, so let's see what the problem wants us to do. What are the horizontal and vertical components of the ball as it leaves the bat? All right, well, we know that the x component is equal to the resultant times the cosine of our angle theta. So we'll plug that in. So we have 23 meters per second times the cosine of 55 degrees. Use our calculator, and we find that the horizontal piece of our velocity is 13.2 meters per second. All right, so I'm going to put that over in my table. All right, now we're going to repeat, all right, but we're going to be looking at vertical motion. So again, it's the resultant, but this times the sine of our angle. So our 23 meters per second times the sine of 55 degrees. And we find that our vertical component is 18.8 meters per second. Now this is the initial, so I'm going to put it up in this upper box, 18.8 meters per second. Okay, all right, so we've got our components. All right, now how long was the ball in the air? So we want to know what was the time that the ball was in the air. All right, so this is where it gets a little tricky. Now the time, this number, you can solve using the horizontal components or the vertical components. It depends on what you know. All right. The easiest way this time is I know the change in position and the velocity horizontally, and I know that the average velocity is equal to that change in position divided by time. So that formula, I have everything I need because the velocity value horizontally is constant. The average is just the same number, 13.2. All right, so if I rearrange and solve this equation, I'm going to have time equal to the distance horizontally, which is 94 meters, divided by my 13.2 meters per second, the velocity value. Plug that into my calculator, and I find that the ball is going to be in the air 7.1 seconds. All right. All right, so now what is the velocity of the ball when it lands in the stands? All right, so this is a little bit tricky because when it lands in the stands, right, that means it's going to be coming down like this, right? We're looking for this resultant value, all right, which means we need to figure out what our two components are, and then we're going to use Pythagorean's theorem to calculate that resultant. All right, so I'm going to have my velocity in the y direction and then my velocity in the x. Now, my horizontal velocity I know because it's constant, so it's still 13.2 meters per second. But my vertical velocity I do not know. I can't make an assumption that it's negative 18.8 because the ball's landing at a different height from where it was thrown. All right, so how do we fix that? How do we solve this problem? All right, we're going to have to first find our y velocity final, all right, as it gets to the stands, okay? So how am I going to do that? What do I know? All right, well, I know that the change in position is 10 meters, all right? And I do have an initial velocity of 18.8, and I know the time, All right, so I'm going to use my v squared formula. So the final velocity squared equals the initial velocity squared plus 2 times the acceleration times that change in position. All right, so v final is going to be equal to 18.8 meters per second. Oh, not squared. The square goes on the outside. Sorry about that. Squared plus 2 times negative 10. I'll be using negative 10 in this calculation. And then a positive 10 meters. It's positive because the ball goes up. It lands higher than where it was launched. All right, so we plug all that in, and we find that the square root is going to give us a final velocity value of 12.4 meters per second. So there is our v vertical final. All right, I have my v horizontal final. So now I'm going to calculate the resultant value. All right, so that resultant value is equal to the square root of vx squared plus vy squared. All right, so we're going to plug those values in. All right, so we've got 12.4 meters per second squared plus 12.3 meters per second squared. We plug all that in, and we find that our resultant velocity is 18.1 meters per second. All right, now we know that velocity requires direction as well. All right, so we're going to use our inverse tangent formula, all right, where theta is going to be equal to the inverse tangent of the y velocity divided by the x. All right, so tangent inverse is equal to 12.4 meters per second divided by 13.2 meters per second. Oh, whoops, I see I made an error up here. All right, my calculation's okay. I did these earlier. This should be This should be 13.2. Sorry about that. The 18.1 is good. I just wrote it in wrong. All right, now one thing I should mention here is this vertical velocity is downward, so that means that's going to be negative. It doesn't affect our use of Pythagorean's theorem because the negative gets squared and becomes a positive, but it is important in our theta calculation. So I need to put in a negative 12.4 divided by 13.2. And when I do that, I find that the angle is a negative 43.2 degrees. All right, so this is the same thing as saying that we have a velocity of 18.1 meters per second at 43.2 degrees south of east. All right, and we're just going to stay over the east quadrant unless it tells us otherwise. All right, so this is the actual velocity at which the ball lands in the stands. Okay? All right, so that's just one example. I'm going to do a couple other screencasts where we'll do some different problem types. The key, though, is this graphic organizer. Cannot emphasize enough how important it is to keep these different components separated. And this organizer is very handy to help you do that. Okay? All right.